Okay. Good evening, everyone. Yeah. Good evening. Yeah. So I'll share my screen. 1 second. Yep. Okay. So today we are going to discuss two topics today. The two topics are permutation combinations and probability. Okay. Yeah. So first PNC, then probability. Yeah. So now in PNC, first thing first. So let me just briefly, okay, go through the formula or whatever is required. Okay. Yeah. So in PNC, you have the whole of PNC. You can actually divide it into two parts. Okay. So one is selection and other one is arrangement. Okay. So selection means here, so you are selecting from some set of objects. Okay. So some set of objects are given. You know the difference, right, between selection and arrangement. Okay. So I'm not going that much deep also. Just whatever the formulas and things which you need for the exam. No? Those things I want to explain. Now, selection you can do from distinct objects or there can be identical objects. Okay. Two things. Or there can be a mix of these two also. Some distinct objects are there, some identical objects are there. So for example, if you have n distinct objects, okay. So that means n different size, whatever objects are there. Okay. From this, if you want to select R, then what is the number of ways you can do it? It is NCR. If you have n distinct objects, you have to select R objects from there. Then you use this basic combination, C for combination, basic combination, that is selection, NCR. Okay. Let's say you have identical objects. Okay. Then how to do? So that means, let's say you have some 4 red balls. Okay. Or let's say 20 white balls. Okay. And 7 blue balls. Okay. So here I have given the number, na? The quantity, how many red balls are there, how many white balls are there, how many black balls are there, blue or black, whatever. Okay. So they all are identical. All the red balls are identical, all white and all black. Okay. Now let's say I have given the numbers. Let's say they are infinite are there. Okay. The number one is little complicated. We'll come to that. But let's say infinite are there. Okay. So there is a huge pool of red balls, white balls, and black balls. Now I need to select 7 balls. Okay. From this pool, how many balls I have to select? 7. Now, how many different ways I can select 7 balls, or I can choose 7? How many ways I can have? How many different selections of 7 balls can be done? That is the question. That means if you are selecting 7 balls, all 7 can be red. One possibility. Don't think 4 red balls are there, infinite now. Okay. Or let's say 2 white are there, 1 black is there, and 4 red are there. So like this, you can make many different combinations, no, of 7 balls. How many such combinations are there? How many such selections are possible? The number of such combinations will be number of such selections. No? So for that only, we use something like, okay, we call it as beggar method, or you can say multinomial one. That is, if X is the number of red balls in your selections, and Y is number of white balls in the selection, and Z is number of black balls in the selection. Now, once you select 7 balls from this pool, then it means indirectly X plus Y plus Z must be 7. Correct? You're selecting 7. Okay. So the number of different selections is equivalent to number of different solutions for this. Now you may say, sir, there are infinite solutions. Now for that one, X plus Y plus Z is equals to 7. I'll come to that. Now if I ask you X plus Y is equals to 3, how many solutions are there? Yes, infinite solutions are there. But if I keep a condition, X, Y must be whole numbers. That means X can be 0, then Y can be 3, 1, then 2, 2, then 1, 3, then 0. Only 4 solutions are there. No? So here also, you can't select 1.1 red balls, no? Or minus 3.5 red balls. So what is the condition here? X, Y, Z belongs to whole number. So you will come across these kind of, whenever you are doing selection from identical objects, okay? You will come across this problem statement. How many solutions are there for this equation if X, Y, Z are what here? Whole numbers. That is the question now. So for that only we have a formula. That is, general formula is, if x1 plus x2 plus x3 plus so on till x r, you can say r is equals to n. So your r different types of identical objects are there. R colors are there here in this case. Okay. The sum of all the colors must be n. That means you are selecting how many objects? N objects. Correct? So now the formula will be n plus r minus 1, c r minus 1. So number of solutions. Number of whole number solutions will be this. Now, for example, if the condition is when you are selecting these 7 balls, every time in the selection, at least one red must be there, at least one white must be there, at least one black must be there. That means your X must be at least 1, Y must be at least 1, Z must be at least 1. That is the condition here. Okay. Then in that case, X, Y, Z, if they are starting from 1, that means they are natural numbers. So number of natural number solutions will be for that equation. Then you have to search for natural number solutions. That means X, Y, Z, everything natural number. Here, 1, 2, X1, X2, X3, XR, all must be natural numbers. Okay, N minus 1, CR minus 1. Okay, remember these two formulae. Now, for example, in this case, X, Y, Z are whole numbers. What will be the answer? 7 plus 3 minus 1. 7 is the right hand side, 3 is the number of variables which are involved. C3 minus 1. So you will get how much here? 9C2. Okay, now like that. Next, arrangement. When it comes to arrangement, again, two different categories are there. Arrangement of identical and arrangement of distinct objects, arrangement of distinct plus identical, you can say. Okay, so distinct objects very easy. R objects are there, or you can say N objects are there, and N places are there. The number of ways of arrangement, very easy. This N factorial only. So if you have N distinct objects, okay, N objects means distinct objects here. So let's say you have a green color, one coin is there, and you have a red color coin. Let's say you have orange color coin, okay, and a blue color coin. Now these 4 coins have to be placed in 3 places and arranged. So when you are placing these coins in these 3 places means the order matters, na? Okay, order matters in arrangement. So what you do? So here 2 processes are involved. First thing, you need to select 3. Correct. That is what you do, na? When I tell you to arrange 3 of them in these 3 places, you will select 3 and then arrange 3. Arrange that 3. Okay. How many ways can you select 3 objects from this 4? Already we have seen that is 4C3. From 4 distinct objects, you need to select 3. And then arrange that 3. Those 3 must be arranged in these 3 places. That is 3 factorial. Like that. So number of ways in which you can arrange n objects in n places is n factorial. So 3 objects in 3 places will be 3 factorial. Okay. So you would have noticed I'm not using the formula np3 because I don't use it, okay, in any problem, because this is the way you need to understand. Okay, so whenever you need to complete a task, okay, this is your final task. In completing the task, you have some minor tasks. Okay, once you think like this, na, let's say this task can be done in some n1 ways, this n2 ways, this n3 ways. If you do all these 3 tasks, then only your final task is achieved, let's say. Then total number of ways in which you can do this is n1 into n2 into n3. That's all. Always think like that in PMC. Okay. Now, next. Distinct as well as identical. That means if there are 3 identical, let's say red balls are there and 2 violet are there and 4 blue are there, let's say, and just one more color. Yeah, 3 green are there. So when you are arranging them, okay, how many are there? 3 plus 2, 3 plus 2 plus 4 plus 3. Okay, so I think it is 12. So total number of objects are 12, of which 3 are identical of first type, and then 2 are identical of second type, and 4 are identical of third type, and then 3 are identical of fourth type. See, you understand what is meant by type, no? They all are one kind, like that. Okay, so first type is red, like that. Okay, so let's change this little bit. Okay, let's say I have one more yellow ball is there and one more pink ball is there. Okay, so now the total number of objects are how many? Total number is 14 now. Okay, and then you have 2 objects which are distinct. Okay, now whichever identical objects are there, the number of identical objects are these, na? So the total number of arranging these 14 objects in a line, if these 14 objects were distinct, then the answer would have been 14 factorial. But now, since some of them are identical, the answer will be 14 factorial by, now first type, how many are there? 3. 3 factorial. Second type, 2 factorial. Third type, 4 factorial. Fourth type, 3 factorial. That's all. Okay? Yeah. Now, let us start solving the questions. Yeah. See, during a draw of lottery, there is a lottery, tickets from 1 to 40. Okay, lottery ticket numbers are 1 to 40. 6 tickets are drawn and then arranged in the what order? Descending order. Okay. So you're drawing 6 tickets and then arranging them in descending order of whatever number which is there on that lottery ticket. Okay. In how many ways it is possible to have 4th ticket bearing the number 25? So when you arrange like this decreasing order, then anything you can have any one of the 40 numbers in like these places. Now what they are saying is, when you are arranging in decreasing order, the 4th ticket must be having number 25. So how many different scenarios this will happen, they are asking. Okay, fine. Now, if the fourth number is 25, in these three places, the numbers which are occurring, it should be more than 25. That is, it can be 26 or 27 or 28 or 29 or 30. Correct? Now here in this two digits, two places, the tickets must be anywhere from 1, 2, 3, so on till 24. Okay. Now it is like from this 5 tickets, you need to select 3 tickets. How many ways you can do? 5C3. So let's take 3. Let us choose 3. The 3 which we are choosing is 26, 28, 29. Let's say. Okay. Now after selecting these 3, I need to place them in these 3 places. Then only the task will be complete. What is your final task? Final task is identify the remaining 5. Your remaining 5 places must be filled. Na? That is your final task. So for filling the remaining 5 places, first what we have identified, what are the possible ticket numbers by which we can replace those places. Okay. Second, what we have done, from those possible ticket places, we have selected. Okay, according to 3 places are there, 3 we have selected. Here 2 places are there. From this 24, you need to select 2. So 24 C2. Now I need to place these 3 tickets in these 3 places. How many ways can I do that? If you are saying 3 factorial, then it is wrong. Okay, it is one way only. This is selection. This is arrangement. Why it is only one way? Because there is a restriction. What is a restriction? It should be in decreasing order. Na? So whenever you select 3 numbers, in how many ways you can place them in 3 places such that they should be in decreasing order? Only one way, right? 29, 28, 26, that's all. Here 29 must come, here 28, 26 in our selection. You can't randomly do that, no? Because the condition is it must be in decreasing. That's all. So now here also these 2 can be placed in those 2 places in one way. Okay. Now to finish this final task, both of them must be done. So the final answer must be 5C3 into 24C2. Okay. Like that. See, the whole of PNC, every aspect, everything covering may be difficult. Okay. But you see the approach, okay, in the questions. Next. This is okay. Yeah. See, what they are saying is, this is previous J mains question. There is a set. Okay. 12 elements are there. So it is partitioned. That means you are dividing it. Yeah, sorry. So with this question, I remembered. Actually, there is one more concept of that is called grouping. Okay. So you are making groups. Let's say, so this I'll just give the formula, then I will come to the question. So it is like this. Let's say in a class, there are 6 students are there. Okay, student 1, student 2, student 3, student 4, student 5, student 6. Okay, the teacher has asked the class leader, that is you, to divide these 6 students into 2 equal groups, team A, team B. Now there, she didn't tell you that names must be given. Okay, just she told, okay, I'll go to staff room and come. By then, you divide these 6 students into 2 groups. Okay, you will not be naming them. So what you will do? There are many ways you can do it. How many different ways you can do it? That is the question. Okay. So if you're doing it into 2 groups, that means in each group 3 students must be there. So that means from the 6 students, if I select 3 students, then that will be first group. Let's say you are thinking like this. Logic is from the 6 students, I will select 3 students. How many different ways I can do that? 6C3. So that many different first groups will be there. That means groups I can make, you may say. Okay, let us list down some of them. S1, S2, S3, but that is wrong. 63 is not correct. S4, S5, S6. Now S2, S4, S7, remaining S1, S3, S5. 7 will not be there, 6 only. No? Okay. So you are keep on doing it. Now, how many rows will come? 63 rows will come. That is okay, correct. But let's say S4, S5, S6 you have selected. Then S1, S2, S3 will be in the, but both are same only. Na? The first group which you have made and this grouping, both are same. You are just making those three students stand in a different place. Doesn't mean the groups are different. No? Why? Because you are not naming them. Okay. When you are grouping also, there are two scenarios. One is naming them. Other one is not naming them. Always the procedure is first to do this, then do this. Okay. Even if the question is name them. First you do it, remember the formula for not naming. The naming is easy only. Why? Because if you have 4 groups, let's say there are 4 groups, group 1, group 2, group 3, 4 groups are again, no naming. Na? 4 groups are there. How many different ways these 4 groups can be named? You with 4 letters A, B, C, D, 4 factorial. Na? It is like placing these 4 objects in these 4 places. How many ways you can do that? 4 factorial. So when you want to name, you just multiply this number with 4 factorial. Okay, let us see the formula now. Okay. So here in this case, the answer will be, the question which I asked is, there are 6 students and you are dividing them into 2 groups. How many different ways you can do that? The answer is actually 63 by 2 factorial. Okay. Now if you start naming them, how many ways 2 groups can be named? 2 factorial. So if you are naming it, then 63 is correct. Without naming, if you are just dividing them into groups, then how many ways it can be done? 63 by 2 factorial. Now I'll just give you some more examples. Then you will understand the formula. Okay. What is the formula which I'm using for grouping? There are 10 students. Now I want to make a group of 2, 2, 3. Okay, let us make it not 10 students, 11 students. And one group of 4. So now the answer will be, total how many students are there? 11 students are there. Okay. Now, these are what are the number of students in each group. Okay. Now multiply all of those factorials. Now, if there is any repetition in the denominator, that is 2 factorial is coming how many times? 2 times. Then write 2 factorial. 3 factorial is coming how many times? 1 time. So 1 factorial. 4 factorial is coming how many times? 1 time. So 1 factorial. That's all. So this is the number of groups which can be formed using 11 students, such that the group number of students in each group is 2, 2, 3, and 4, like that. Let's say I have 12 students. I'm making groups like this. Okay. The size of the group is 2, 2, 2, 3, 3. That means 3 groups are having 2 students and 2 groups are having 3 students. So then total is how much here? 12 by. Now all this 2 factorial, 2 factorial, 2 factorial, 3 factorial. Size of the groups I am multiplying. Then you see how many 2 factorials are there? 3. So because 2 factorials are there, we need to write 3 factorial. How many 3 factorials are there? 2 are there. So write 2 factorial. That's all. Okay. So if I want to make groups of 5 groups of 2, 2, 2, 2, 2, then the answer will be 10 factorial by 2, 2, 2, 2, 2, 5 times. Then 2 factorial is coming 5 times. So 5 factorial. Okay. Like that. Now, in each of these cases, if you have to name them, okay, then with name, I need to just multiply. How many groups you are making? 4 groups. So 4 factorial. Here, how many groups you are making? 5 groups. So into 5 factorial. Here, how many groups you are making? 5 groups. So into 5 factorial, like that. You have to make them into groups and then you have to name it, let's say. Then you have to multiply with the number of groups you are making factorial. Okay. Fine. Let us come to this question. So the set is there. Set is what your collection of objects. So there are 12 objects. Okay. That is partitioned into 3 sets A, B, C, and all are of equal size. So you are making these 12 objects. You are forming 3 sets. That means you are forming 3 groups indirectly. Okay. What is the size of each group? 4. 4, 4, 4. 12 objects are there. Okay. But there are some restrictions. What are those? A union B union C must be S. That means if you make union of these, then it must be, you should have this set back. Okay. Very good. Next, what does that mean? All the 12 objects are divided into, are used in division. Okay. See, for example, let's say, I can make this set A, which is 1, 2, 3, 4. Let's say set B can be written using S only. We are making the set, na? 2, 3, 5, 6. Now, did you notice what is the difference between this question and the grouping which we have seen? In grouping, student 1 can't be in both the groups, na? But in sets, 1 is the, let's say if I take 2, 2 is an element of the set S. 2 can be in both A and B, because what they are saying, you are making A, B, C from that set. In set, repetition of objects, yeah, you can have, na? But you will just represent it like only one. Okay, fine. Coming to that. But later on, they will clear the doubt. You see, what is that? Intersection must be null set. That means this common thing should not be there, they mentioned. Okay. So which means it is same as making groups of people only. When you're making groups of people, there won't be any intersection between the two groups. No? Okay. So indirectly they are saying this 12 objects which are there, 1, 2, 3, 4, so on till 12. You have to make it into how many groups? 3 groups. 3 sets means 3 groups. Okay. Of this, how many ways you can do that? 12 factorial by 4, 4, 4. So 4 factorial into 4 factorial into 4 factorial. Then 3 are there. So 3 factorial. Okay. You are just doing the partition. That's all. Then, so finally, what will be the answer? 12 factorial by 4 factorial whole cube into 3 factorial. Next. All this divisibility, it's okay. Yeah. So that is the all the concepts which are there. Okay. There will be so many questions based on that. Okay. Now we will see a bit of probability. Okay. So in PNC, the questions which are coming in the exam are only from these 5 categories: selection, arrangement, grouping. Okay. Like that. Okay. When it comes to probability. Okay. Simple guys, probability chapter can be, you can say like this. Okay. See, you should understand these things. Main importantly in exam what are coming, I'm concentrating on that. You should know what is independent and dependent events. At least you should understand now how to identify two events are independent or dependent. Next. Obviously, conditional probability from there only you will get it. Okay, that is not actually what I wanted to know. Right? Total probability, Bayes theorem, and finally binomial theorem of probability. Okay, simple. First, independent and dependent. Okay. See, I just want to give a different direction, matlab, the direction in which normally the probability questions and everything must be approached. I just want to give the direction, because if you start doing questions of probability, you know how many are there. Okay, loads and loads, and each one will be different also. Okay, so general concept of probability is like this. First thing, there is something called event set, no? So your random experiment means something is happening. Okay, some like rolling of dice or tossing a coin. Okay, or picking a card, picking two cards. Okay, picking three cards one by one after replacement, picking three cards one by one without replacement. All these are some random experiments. Okay, so the outcomes of the random experiment which are there, you will write it as in a set. For example, if it is tossing a coin, simple, heads and tails. Okay, if you're tossing a coin till it gets head, you keep tossing it till you get head, then your outcome can be head, tail, head, tail, tail, head, tail, 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 head. You can't have four tails and then head, then tail. You'll stop it there, no? So like that. What I want to say is, for every random experiment, you can write this. Okay, we call it as what here? Sample space. For every random experiment, you can actually write it. Okay, whatever may be the random experiment, like they will give in probability some questions, na? That in a family, there are five boys and let's say three girls are there. How many ways can you select two kids? Okay, then what will be your sample space? The sample space will be either you can select two boys, boy, girl, that's all, or girl, girl. Like this, you can write the sample space. No? Now, the important part here is the individual, whatever things are there here in the, whatever I'm writing in the sample space, they are called outcomes. For example, in this question, if I ask you, okay, tell me what is the probability that if I select two kids from this family, both of them are boys. Obviously, the answer is not 1 by 3. Okay, because if you're selecting two people, then the chances are not equal. Na? Getting both of them as boys, one boy, one girl, and girl and girl. Okay, so so these outcomes have different probability, na? P1, P2, and P3. So since P1, since this term is important, P1 is not equals to P2 or P3, and the same way. So not all three are not same, na? Since P1, P2, P3, all three are not same, then what do we call this outcomes? Not equally likely. Okay. So these three outcomes are not equally likely. For example, if I ask you, I'm selecting I'm selecting two kids from this family. Find the probability of having a boy in it. Then which means, which outcomes will satisfy this one? Having a boy in it means these two. So what is the probability of getting BB? P1. What is the probability of getting BG? P2. So the probability of having a boy in it will be P1 plus P2. That's all. Whatever complicated problem is there, okay? If you can write the sample space, you can simply add like this, P1 plus P2. At least one girl means P2 plus P3. Now, individually, this outcome probabilities you should be able to find. What is the probability of having both of them boys? So 5C2, from five boys, you are getting two boys. That is the favorable outcome. Na? Total will be from 8, any two you are selecting. That's all. That is P1. P2 like that you can write. Okay. P2 will be one boy and one girl must be selected. That is 5C1 from 5-1 and from 3 girls 1. From total possible ways of 8C2. Like that. Okay. Fine. Next. Total probability and Bayes theorem together we can discuss. Okay. How means I'll tell you. Let me use up this space. Yeah. See, how you can say is, this is like a detective question, detective problem. When your Bayes theorem is a detective problem, correct? So while I am explaining Bayes theorem, you will understand total probability also. Bayes theorem is detective problem means, for example, let's say in your city, there was a crime which is conducted. Okay. And in that city, there are two gangs. There will be some names na, for that gang. Okay. So let us just not give the fancy names. Let's just say gang A and gang B. Okay. Two gangs are there. So immediately after the police, you are the police officer, you got the call. Okay, fine. There was some murder is which is reported means immediately you will have it. So generally assume that in general real life situation there can be many different gangs which are there. Okay, but for the simplicity of this question, I have just told two gangs. Okay, and other than people from these two gangs, the other people will not commit the crime. Let's say. Assume those things. Okay, now so you will think that okay, which one? So then you will ask some details. What you will do? You will do investigation. Na? You will go for and ask for some details there. Then they told ki okay, these are the details which they told. Okay, the people who have come, they come by car. Okay, that is one detail you have got from the people. And the people who have come for doing this murder, they used gun. You got that from the that like viewing the dead body that they have used gun. Okay, fine. So with these two, let's say gang A is responsible for 70% of crimes in the city, and gang B is responsible for 30% of the crime in city. Initially, when you got a call, you will suspect gang A would have done the murder. Yes. Okay. But now, after investigation, what is the purpose of investigation? You will get more okay precise information, right or not? Your probabilities of finding the thief will be more okay after the investigation than before that. Okay, now let us see the patterns. Gang A does this is historical data. Now I am giving the complete question to you. Okay, that is gang A. So now this is information. Next comes question. Gang A previously historically if you see they travel mostly by bike only. In 80% of the cases, they travel by bike and they do the murder. In 20% cases, sorry, yeah, they do the murder by traveling with car. Okay, they go on car and do the murder in only 20% of the situations. Okay, and gang B, they use mostly bike, sorry, car only. In 90% of the situations they use car. In 10% of the situations they use bike. Okay, that is about the vehicle. When it comes to types of murder, gang A normally, generally they do a lot of the murders with knife only, not gun. Okay, that is 90% of the murders they do with knife only. Only 10% of the murders they do it with gun. And whereas gang B, they do 70% of the murders with gun and 30% of the murders with knife. Now you are a detective or no, whatever, okay, name you want to give. So this is history. Now you understood the crime scene, no? That in the crime scene there was car which was found before the murder at the time of murder, and the gun was used. Now this is historical data. Initially, if this without this information, your guess would have been gang A has done the murder. What is the probability gang A to be doing the murder? 0.7. What is the probability that gang B has done the murder? 0.3. This is before the information. No? Now, once the information comes in, you should not give again 0.7 and 0.3. Okay. Now, how we will, let us see. So it is like this. The murder has happened. It could have been from gang A or gang B. So what is the probability that it is from gang A? 0.7. This is before any information. And what is the probability that it is from gang B? 0.3. Okay. Now, if gang A has done the murder, then what is the probability that they would have used a bike? What is the probability that they have used a car? What is the probability they have used a bike? 0.8. What is the probability that they have used a car? 0.2. Same way, if gang B has done the murder, then what is the probability that they have used a bike? It is 0.1. Okay. What is the probability that they have used a car? From this historical information, I am writing them. Okay. What is the probability they have used a car? 0.9. Okay. Now there is one more level of information. Okay. So let us do one simple question first. Then we'll go to the next level. So let us say only this part is the information. And again, let us not bother about the gun. Only one thing is at the crime scene, car is seen. Okay. So now this path, what does it mean? This path, if I'm going, this orange color one, that means what is the probability that gang A has done the murder using the bike? Okay, that is 0.7. What is the probability gang A has done the murder? 0.7. No? Using bike means 0.7 into 0.8, like that. What is the probability that gang A has done the murder with using car? 0.7 into 0.2, like that. That is the meaning of that complete path. Okay. Now here in this question, now the investigation question is what here? On the crime scene, what you have seen? You have seen a car. So tick mark that one, car. Now what you do is, you just see what paths are leading to that car, whichever option you have ticked. This is one path. This is like that. Okay. Now, if you start writing 0.7 into 0.2, that means in that branch you multiply them. Across the branches, you add all those 0.3 into 0.9. I have written some number here. Okay. What is this number? We'll come to that. Okay. With this, you will reach the outcome of car. Now, if the question is like this, now you're a detective. Now, what question I will ask finally? Let us not forget the question from the beginning. What is the probability that this murder has been done by gang A? Okay. So this pink color, whatever are there, that is the total possible paths onto the given scenario. That is murder with car. What is the contribution from this branch you have to see? What is the contribution? 0.7 into 0.2. Because what is my question? What is the probability that the murder is done by gang A? Okay. So then this is denominator is only total probability. Okay. Fine. So how did I write the denominator? Let me just explain. Denominator is written based on the observation, what is observed. Okay. So here the observation is, in the crime scene, the car was found during the murder. Okay. Some witness has told car was there during the murder. So based on the information, interrogation, or forensic information or whatever it is, you write the denominator. Okay. So the denominator will have a lot of contributions, branches. The branch coming from gang A is there. The branch coming from gang B is also there. Okay. Now the contribution from gang A, the branch coming from gang A, that will tell you the probability that gang A is the suspect. Okay. This is the interrogation question only. No? So that is how you will see the questions of what here? Bayes theorem. Something has happened. Like I will tell you common questions. There are 3 urns. Okay. First urn means a bag, 3 white and 2 black. Second bag has 4 white and 1 black. Third one, 1 white and 4 black. Okay. Now what you are doing is you are selecting one ball and you have found it to be black. You have selected one ball and found to be black. Now the investigation information is this only, no? You have found a black ball. Okay, after selection. Now I am asking you the question: what is the probability that it has come from bag 1? Okay, what is the probability that this black ball which you got finally, it is from bag 1? Okay, so what you do? So 3 bags are there. First thing is what you're selecting a bag. Now they have not given anything, so 1/3 probability here I am writing. Because any bag you can select, no? At random you are selecting. Now here the probabilities which I have given initially is what here? 0.7 and 0.3. There I have given 1/3, 1/3, 1/3. Here why I have given 0.7 and 0.3? Because historical data says if there is a murder which has happened, there is 70% chance that it is from gang A and 30% that it is from gang B. So 70% of the time path A will happen, 30% of the time second path will happen. But here equally probable, no? all 3 paths. That means I can select bag 1 or bag 2 or bag 3, equal probability. Now after selecting bag 1, now on which I have to put a tick mark on what has happened. That means what has happened, you are selecting a ball and it is found to be black. So black I will write, and other one is not black. If you're selecting, it may be white or whatever it may be. Okay, so because I am only worried about this tick mark, so here also one black will come, other one is not black. Okay, I will not even fill them because we are not using those branches, na? Black, that's it. Now from the bag 1, what is the probability here of getting a black ball? It is 2/5. From second bag, what is the probability it is a black ball? If you're selecting 1/5, 4/5. Okay. Now, what are the branches which contribute for our outcome? This branch, this branch, this branch. Now, let's say if my question is like this. Let's say there are 3 bags with some XYZ content. That means this content. Okay. You are randomly selecting one bag and then selecting a ball. What is the probability that the ball which you select is of black color? That means what is the probability that this paths would have been chosen? What you will say? That is 1/3 into 2/5 plus 1/3 into 1/5 plus 1/3 into 4/5. What is this? Whatever final answer which is there, this is the probability that when you select a bag and a ball, that ball is black. Okay. This is only total probability. But now what is the question? The question is the ball is found to be black. Now this becomes then observation or information. They're asking what is the probability that it is coming from bag 1. So that means what is the contribution from this branch? What is the contribution from that branch? 1/3 into 2/5. That's all. This is what here the probability that black ball which you are getting at the end is from first bag. That's all. That is only Bayes theorem, and whatever is in the denominator, that is only what your total probability. Okay. Now, last, what is there? Binomial theorem of probability. This is simple formula only. If you are repeating the random experiment, this is the case where you will be repeating the random experiment many number of times. Okay. Tossing a coin repeatedly 10 times you are tossing. That means your random experiment is tossing a coin. You are doing it 10 times like that. So if you repeat a random experiment n times and clearly the success and failure is defined beforehand. Now, when you're tossing a coin, what is success? What is failure? There is nothing defined. No? If head is a success, getting a head is a success, tail is a failure, then it is defined. Okay. Success means getting a head. So for every random experiment, some outcomes determine success, some outcomes is failure, for example. So probability of success is P, probability of the failure is will be 1 minus P. Correct? Total must be 1 only. No? Okay. So then the probability of R success. I'll just tell you the meaning of it. For example, if you're tossing a coin 10 times, are you sure every time 5 head and 5 tail will come? Obviously not. No? Okay. It's not like 10 times you try to toss, every time 5 heads and 5 tails will come. No, no. Okay. If I ask you, if I'm tossing a coin 10 times, can I get 10 heads? You'll say, yes, can I get 10 heads? Yes. It's not impossible. No? You can get 10 heads. But the probability of that happening will be less. Now, what is that probability? What is the probability that I will get 10 hits? That is only this one, no? Whatever I am writing. The probability of R success. If getting hits is a success, then probability of R 10 success here. And how many times you are conducting the random experiment? 10 times. So your N is 10 and R is 10. And what is the probability of success? 1 by 2. Na? Getting a hit is a success in this case. For example, if you are rolling a dice, let's say the success is getting 1 and 5. Failure is getting 2, 4, 2, 3, 4, 6. So what is the probability of success? 2 by 6. That is 1 by 3. That is 2 outcomes by 6 outcomes. Like that. So probability of getting R success when you repeat a random experiment n times is NCR into P power R into 1 minus P power n minus R. That's all. Okay. Fine. So I'll share this document, guys. Actually, the questions are there for practice. Okay. Because, like PNC probability, it is weightage is less, but only from selected. Okay. If the question is easy, it will be very easy in the exam. Otherwise, it will be very tough. So that's why I've chosen my explanation to some parts of theory only today, not the questions and all, because the questions are infinite. Well, it's a big ocean pool in PNC and probability. Okay. So at least with theory, I can cover something. No? Okay. Fine. So next, the topic which will be there for the next class, what is remaining is complex numbers and that stuff, some remaining ones. Okay. Acha. Ashika has told, yeah, in the ticket problem, it was 40 tickets. Na? I just 30 has printed in my mind. So I used 30 the whole question. So same thing you can do for 40. Okay. Yeah. Fine. Okay, guys. So that's it for today. So tomorrow you'll have questions on complex numbers. Okay. Fine. Okay. Thank you, everyone. Okay. Thank you, guys.